In this lecture video, we're going to be looking at custom hypothesis test in the Latin square design. We'll start by looking at the general form of hypothesis test that will be available. We'll then look specifically at hypothesis tests involving differences between two treatment means. We'll generalize that then to hypothesis tests involving contrasts of two or more treatment means. We'll generalize further to look at hypothesis tests involving non-contrast linear combinations of one or more treatment means. And then we'll look at a special case of that involving hypothesis test for individual treatment means. So let's first look at the general form of the hypothesis test that we're going to be looking at in this lecture. In general, hypothesis test in this collection of tests will involve a linear combination of the treatment means of the form given here, a sum of a sub k times mu sub k, k ranging from 1 up to p, where p is the number of treatments. The hypothesized value of such a linear combination will be denoted by lowercase lambda sub 0, which will stand in some relation to the linear combination of the treatment means in the hypotheses. As usual, there will be two-tailed tests, left-tailed tests, and right-tailed tests available to us. The general form of the test statistic for this collection of tests will be denoted by t-calc, and in general, it's going to be the ratio of the difference between the estimated value of the linear combination and the hypothesized value, lambda sub 0, divided by the estimated standard deviation or standard error of the estimator of the linear combination itself. The specific form of the test statistic, and in particular the denominator, will depend on the expression for the estimated standard error of the point estimator for the linear combination, which will depend on the nature of the linear combination being tested. In some situations, the actual reference distribution will be known, and therefore the appropriate critical point will therefore also be known and available and calculable. In other situations, the actual reference distribution will not be known, and therefore the actual critical point will be unknown as well. This will require finding an approximate critical point using one of the two approximation methods that we've been looking at. Whether or not the actual reference distribution is known will depend on the nature of the linear combination about which we're testing, which in turn will determine the sampling distribution of the test statistic, which under the conditions of the null hypothesis determines the reference distribution for the test. Now let's look at the specific situation where we're testing hypotheses involving differences between two treatment means. And so there are three sets of hypotheses that we can test. We have a two-tailed test available, a left-tailed test, and a right-tailed test. And so you've seen these kinds of hypotheses before, and so there's really nothing new here. The specific form of the test statistic in this situation is given by the following. And you can see here that the estimator of the difference between mu sub k and mu sub k prime is the difference between the estimated values of those treatment means. So mu hat sub k minus mu hat sub k prime. From that, we subtract off the hypothesized value of that difference, which is denoted by lambda sub 0. And then in this case, the estimated standard deviation for this estimated difference is equal to the square root of 2 times the MSE from the ANOVA table divided by p. Now the rejection criteria depend on the form of the test. If it's a two-tailed test, we have a two-tailed rejection region. If it's a left-tailed test, we're going to reject for small values of the test statistic t-calc. And if it's a right-tailed test, we reject for large values of the test statistic. The thing to note here is that in each case, the number of degrees of freedom for the reference distribution, which is the distribution from which we get the critical point or critical points, is equal to p minus 1 times p minus 2. So for each of these three scenarios, the reference distribution is a student's t-distribution with degrees of freedom equal to p minus 1 times p minus 2. Now, if we happen to be performing a two-tailed test, then there is an equivalent procedure that involves using the F distribution and an F statistic. And the F statistic, F calc, is given by the square of the T calc test statistic in this situation. And so it's going to be given by this expression here. The rejection criteria will be to reject the null hypothesis if this test statistic, F calc, exceeds the upper alpha percentage point of the F distribution with one numerator degree of freedom and denominator degrees of freedom equal to p minus 1 times p minus 2. All right, now let's look at a hypothesis test involving contrasts of two or more treatment means. So this is a generalization of the procedure that we just looked at. And so in this scenario, we have the same three types of hypotheses. We have two-tailed test, a left-tailed test, and a right-tailed test. But now the expression or the linear function of the treatment means that we're testing hypotheses about is denoted by the sum a sub k times mu sub k. But now keep in mind that because this is a contrast, the sum of the a sub k's is going to be equal to 0. Now the specific form of the test statistic for tests involving contrasts of treatment means is given by this expression. The numerator is equal to the difference between the estimated value of the contrast that we are talking about or testing hypotheses about. So the sum of the a sub k's times the mu hat sub k's minus the hypothesized value for the contrast, which is lambda sub 0. The estimated standard error of the point estimate of the linear combination, or the point estimate of the contrast, is equal to the square root of 1 over p times the sum of the squared a values times the MSE. All right, and then the rejection criteria in this scenario, because this is a contrast, it still involves the t distribution with p minus 1 times p minus 2 degrees of freedom. All right, so because this is a contrast, as was the previous situation where we're looking at differences between treatment means, the number of degrees of freedom associated with the reference distribution is the same. Again, if we are performing a two-tailed test, then we can utilize the F statistic version of the test. All right, and so this would be the expression for the F statistic, F calc. And then the rejection criterion would be to reject the null hypothesis if the value of this test statistic is greater than the upper alpha percentage point of the F distribution with one numerator degree of freedom and p minus 1 times p minus 2 denominator degrees of freedom. All right, now let's look at hypothesis test involving non-contrast linear combinations of one or more treatment means. So the hypotheses for this situation look the same as they did for the situation that involved contrasts, but in this case the sum of the a sub k's is not necessarily equal to 0. If the sum of the a sub k's is equal to 0, then we're back in the previous situation, but here we're allowing the sum of the a sub k's to be something different than 0, so that we're looking at something that is not a contrast. All right, so the specific form of the test statistic in this scenario has a numerator that is going to be the same as it was in the previous situation, but the difference is in the denominator, in particular the estimated standard deviation of the point estimator in the numerator, and this is the expression for that estimated standard deviation. So you can see here that it involves the sum of the a sub k's squared. Let me say that, let me be very careful how I say that. For the transcript, it's the square of the sum of the a sub k's, and it also involves the sum of the squared a sub k's. In addition, it involves not only the MSE, but it also involves the mean square for rows and the mean square for columns. All right, and so the general form for the rejection criteria will look similar to what it is for the usual t-test but in this situation, the sampling distribution of t-calc is unknown, and therefore the critical point must be approximated. The same methods of approximation used for constructing confidence intervals are used in the context of hypothesis testing as well, and so these two approximation methods are included on the next two slides. And so approximation method 1 approximates the critical point directly, and this is the formula for that critical point. It is a linear combination of t-values here, and for computing this, we see that the degrees of freedom 1 and degrees of freedom 2 are both equal to p minus 1, and degree of freedom 3 that shows up here is equal to p minus 1 times p minus 2. The values for Q1, Q2, and Q3 are also given here. Incidentally, the values for Q1, Q2, and Q3 for approximation method 1 are the same as they are for approximation method 2, which we have on the following slide. Again, approximation method 2, this is known as Satterthwaite's approximation. And the way this works is that we approximate not the t-value directly, but the degrees of freedom associated with the reference t-distribution, and then we use the t-value, or the critical point, from that particular t-distribution. So in this case, the degrees of freedom associated with the critical point are given by this expression. Again, Q1, Q2, and Q3 are defined as they were on the previous slide. And also, the degrees of freedom are the same as they were on the previous slide, where df1 is p minus 1, df2 is p minus 1, and then the third degree of freedom, df3, is equal to p minus 1 times p minus 2. All right, now let's look at a special case of that testing procedure for hypothesis test for non-contrast linear combinations of treatment means. In particular, we'll be looking at hypothesis tests that involve individual treatment means. And so this is what the hypotheses would look like. Again, we've got a two-tailed test, a left-tailed test, and a right-tailed test. Lambda 0 can be any value that is appropriate and meaningful in the given context. The form of the test statistic in this situation is lambda hat sub k minus, mu hat sub k minus lambda sub 0. And then the estimated standard error of mu hat sub k, this is what shows up in the denominator, it would be the square root of the square of 1 over p times the mean square for rows plus the mean square for columns plus p minus 2 times the mean squared error. The critical points need to be approximated because, again, this is not a contrast, and so not only is the MSE participating in the calculation of the estimated standard error, but also the mean square for rows and the mean square for error. The mean square for rows and the mean square for columns. All right, so because of that, the reference distribution needs to be approximated so that we can get the appropriate critical point. All right, and so you would use those approximation methods that we saw on the previous slide. Okay, so this is a good place to stop this. We will continue on and look at an example in the next lecture video.